Welcome to the another video of the basic electrical engineering, and here we discuss about the instantaneous power output when the load is combination of RL and combination of RC. We will do it together so that you can have a comparison between them, and here we will take the reference as current because the current is there uniform and same through R and L. Here also current is same from R and C. So instead of having the voltage as a reference, we will take the current as a reference. It doesn't matter anything, like only thing is that we will have a reference in the x-axis, we'll have a current, and in some angular deflection we will have a voltage. So let us write the current as a reference over here. So we take the current is same in both the case, and here let us say this is for RL. So let us say I take the value, these two are different values. Here I am talking about like you can have a V supply, Vs, and here also Vs, we can say VSL and VSC for the capacitor. So what we can write is VSL is equals to, we do not know what is the angular change right now, so let us keep it as it is equals to R into I of omega t plus the voltage, this addition will be L d of, so omega is multiplied because we have I of omega t and d of omega t, because we are taking in terms of omega t as the variable and in terms of omega t, so this equation is okay. So when I substitute the value of Im over here, this will be Rim sine of omega t, and this side will be omega L, derivative of sine is, so Im will be written as it is cos omega t. Similarly, when we write here I of omega t is equals to Im sine of omega t, so Vsc is equals to R with I, so we will write here as it is I, because voltage across R is R into I, plus voltage across capacitor is 1 by C integration of I d omega t. So d of, now instead of t we are writing here omega t, so here also we are multiplying omega, so this term will be finally Rim sine of omega t, and here will be have integration of the sine omega t is cos of omega t minus of cos omega t, so we can write here is minus 1 by omega c cos of omega t. We are going to use this equation right now, this term z sine omega t plus phi, it can be something, this term can be written as z sine omega t plus phi, where if anything is written like some constant, if you have the form of cos phi sine omega t or sine phi cos omega t, and z may be any constant, so we can rewrite this type of equation in this term. So you can think that this is the polar form one type of, and this is the x and y component of it. So how we can narrate this is as, suppose here z cos of phi, let us take this for example of this one, so let us write, because here this particular point and this particular thing, it seems like we can rewrite this thing in this equation. So we can write this, taking the Im out from here, we can write here R sine omega t plus omega L cos omega t. So we can take the term R as, because here sine is there, so let us take the R as Z cos of phi, and also we can take this constant omega L as z sine of phi. So we are trying to write these two terms so that we can get now the term here as, instead of r, we are writing z cos phi sine omega t, omega L as z sine phi cos omega t, and we can write here this as Im z sine omega t cos phi cos omega t sine phi. So we can write this as sine of omega t plus phi. We can write like this, and that is the objective of putting this value. So what we can get if we evaluate this, we will see that if we take a ratio between these two, we can get is that sine phi by cos phi is equal to omega L by r, and which also reflects the value of phi. So from here what we get is the phi is equals to tan inverse of omega L by r, and the value of z is, from these two we can also get the value of z is root over of r square. We can show you this thing also. Just you take the square of these terms, so it will be like r square plus omega L whole square is equal to z square cos square phi and z square sin square phi, which gives this cos square plus sin square is 1. So this is z square is equal to r square plus omega L whole square. So from here z is equal root over of r square plus omega L whole square. So you get the value of phi here and the value of z here. So if I substitute here in this, so here I am getting the value of the voltage VSL. So VSL, what I am getting is Im z is, let us put the value of z here, or you can simply write the z term and sine of omega t plus tan inverse of omega L by r. So this is the value of the voltage equation. Let us similarly check what is for the capacitor. So for capacitor we are taking this Im term common here, and here also we are putting the value of r is equal to z, because the sine term, so z should be in cos, and here 1 by omega c is equal to z sine phi. So also you are getting a value here, the term is there, minus term is there, so you can keep in mind minus, or you can put here the minus value, any one is okay. So if we just take this as a positive quantity, this much, and these two quantities we are taking, so accordingly we can have the same expression here with a little bit of difference, that is sine phi by cos of phi will be, so this term first 1 by omega c divided by r, so that will be r. So this is the value we are getting, and we can now rewrite here as Im this thing as z cos phi. Only thing is that minus, here plus is there, here we get minus cos omega t, and here we get here VSC is what we get Im z sine of, instead of omega t plus phi, here we are getting sine of omega t minus phi. So the quantities will be just a difference. There will be difference in the value, that z is now equals to root over of r square plus 1 by omega c whole square, and phi will be tan inverse of 1 by omega cr from here, and we take the square root of this term, so it will be now no longer to prove our entire expression. We can get the value of z and phi like this. So finally we can write VSC is equal to Im, value of the z is r square plus 1 by omega c whole square, and we get sine expression and here minus tan inverse of 1 by omega CR. So we get expression of VSL and VSC here. So now we have the current waveform. Since we have taken the current as a reference here, so we will draw the voltage now. So let us take this quantity as phi, and this is phi is some angle. Let us take this angle as 30 degree. Here also let us take this angle as of 30 degree, so that we can have a common term. And here we get is omega t plus of 30. So it is actually plus of 30 means omega t at minus 30 degree it will start. So if I have that negative waveform of it reflected here, so that I can get the value of minus 30. So I can think about having a voltage waveform starting from here, and obviously it is leading by angle of 30 degree. So we can draw, and here we get a voltage waveform done with a leading 30 degree, and we just this expression is done so that you will also be able to draw the leading 30 degree voltage waveform, and this will look like this. And here we have the voltage waveform again with this peak value. So this peak value, whatever you get, is the peak value is here. Similarly, the IM peak value is here. So here the voltage capacitor peak value is this, and with lag by 30 degree. So voltage is actually lagging here by 30 degree. So we have to draw the voltage waveform with the lag because omega t at 30 degree it will start. So here, and if we take it on the back end side with this current waveform, it was lagging somewhere here. So we draw that expression may not be 100% correct, but this waveform is okay. So this is the voltage waveform that you get here for the capacitor, and the current waveform is taken as a reference. Here also you have a current as a reference, and the voltage waveform what you get is VSL. Usually you have seen that in case of inductor the current is lagging, and if we draw the phasor diagram this concept will be more clear. Let us take the current phasor as the reference, and in the positive x-axis, and this I is obviously is equal to Im by root 2 because these are the RMS quantities. So it is understood as the peak value divided by root 2 only. And you have the voltage waveform which is leading here by 30 degree. So let us say this is a 30 degree angle, and you have the voltage waveform which is leading by an angle of 30 degree. So you have a voltage here. Similarly here the current and the voltage is here lagging by 30 degree. This value is 30 degree. This is 90. So it is lagging by 30 degree. So the voltage is shown at may not be like 100% 30 degrees. Nearly it should look like 30 degree. So here you have a voltage which is, you can represent it by this minus 30 degree, and here it is plus 30 degree. So you will write here V, this V can be written as, if this is VL, you can write this as V angle 30 degree, and this is I angle 0 degree. If is IL, so I angle 0 degree, this is V angle 30 degree. If you would have taken the voltage as a reference, the same statement could have V angle 0 degree, and the current would have I angle minus of 30. So this statement is correct, and this one is also correct. Only thing is which one you are taking the reference. So similarly here the current is leading the voltage by an angle of 30 degree. Here current is lagging the voltage by an angle of 30 degree. So this is both statements will be correct.